In this video, we will focus on the dynamics of wheeled mobile robots. Lagrange method for deriving dynamic equations will be explained. The motion of a mechanical system is related through a set of dynamics equations and the forces or torques the system is subjected to. The study of dynamics is important due to the problem of the control, which is in contact with its environment. Thus, the goal here is to develop a model that can describe the dynamics of the system. In the case of a wheeled mobile robot, the contact with the environment occurs at the contact point between the wheel outer surface and the ground surface. The interaction between these two surfaces has a significant influence over the dynamic motion of the system. Generally, there are two major methods for deriving the dynamic equations of mechanical systems, namely Newton's method that is directly related to the Newton's second law, and the Lagrange method that has its root in the classical work of D'Alembert and Lagrange, which they have worked on analytical mechanics. The main difference between the two methods is the dealing with constraint equations. While Newton's method treats each rigid body separately and explicitly model the constraints through the reactive force required to enforce them, Lagrange provides systematic procedure for eliminating the constraints from the dynamic equations, typically yielding simpler system of equations. Thus, it is not surprising that the majority of the conventional wheeled mobile robot models we found in the literature were developed using Lagrange as a method of choice. A nice thing about the Lagrangian method is that we are free to impose any given constraints at the beginning of the problem, thereby immediately reducing the number of variables. Here is the procedure of the Lagrange approach for formulation of dynamics. In this approach, first a set of coordinates referred as generalized coordinates in the classical dynamics literature is chosen. These parameters parameterize the configuration space of the robot. Once generalized coordinates have been chosen, these can define the generalized force F. The sum of the potential and kinetic energies of all parts of the system are then expressed in terms of generalized coordinates and their time derivatives. The Lagrangian function is defined as sum of the kinetic energies minus sum of potential energies, and it is denoted by L. Lagrangian equals sum of kinetic energies, which is denoted by K, minus sum of the potential energies, that is indicated by P. All the letters are in uppercase. The equations of motion can now express in terms of the Lagrangian, as you can see here. This is the Euler-Lagrange equation, and finally a set of second-order differential equations for the dynamics obtained from this equation. which is expressed in the chosen coordinates for the configuration space. Note that this is Euler-Lagrange equation with external forces. The external force is 0 in the standard form of the Euler-Lagrange equations that you can see in some old literature. We illustrate the Lagrangian dynamics formulation through a simple example. Consider a particle of mass m constrained to move on a vertical line. The particle's configuration space is this vertical line, and a nature choice for the generalized coordinate is the height of the particle, which we denote by the scalar variable x. Suppose that the gravitational force mg acts downward and an external force F is applied upward. By Newton's second law, the equation of motion for the particle is F minus mg equals mx double dot. We now apply the Lagrangian formulation to drive the same result. The kinetic energy is the half of m times x dot to the power 2, and the potential energy is mgx, and the Lagrangian is the kinetic energy minus potential energy, and you can see the relation here. Using equation 1, that is Euler-Lagrange equation, we can obtain the equation of motion. F equals time derivative of partial derivation of L by x dot minus partial derivation of L by x equals mx double dot plus mg. This equation matches with the equation obtained by Newton's approach. In the previous example, we were dealing with a particle, with a simple particle that was free to move. For a mobile robot, derivation of the dynamic model is slightly different. The main difference is the presence of non-holonomic constraints on the generalized coordinates. Next, we will talk about the Lagrange formulation to obtain the dynamic model of n-dimensional mechanical system subject to k kinematic constraints. In the Pfaffian form, we write the constraints as A of q times q dot equals 0, in which q is the vector of generalized coordinates, and the dimension of generalized coordinates is n. The dimension of constraint matrix is k by n. In any case, we assume that the constraints do not work on the robot or on the system. That is, the generalized force denoted by tau con due to the constraint satisfy the equation 2, which is tau con transpose times q dot equals 0. This assumption means that tau con must be a linear combination of the columns of A constraint matrix. That is, tau con equals A transpose lambda. For some lambda, since these are the generalized force that do not work when lambda is subject to the constraints, so we can write tau con transpose times q dot equals transpose of A transpose lambda times q dot, which is equal to lambda transpose times A times q dot equals 0. That is true for all lambda. So the Euler-Lagrange equations can be written as equation 5, in which S of Q is an n by m matrix mapping the m equals n minus k external input tau to generalized forces performing work on Q. Actually, S is an torque or force distribution matrix, or an input distribution matrix. It has been assumed that the number of available inputs do not match the number of degrees of freedom, which is common in the case of wheeled mobile robots. If the number of inputs match the number of degrees of freedom, S would be an identical matrix. Anyway, using equation 3 that you can see here, one can write the equation 6. We replace tau con with A transpose times lambda, and we obtain equation 6. A transpose is the transpose of the constraint matrix. Here lambda is a k-dimensional vector, and we call it vector of Lagrange multipliers. And the term A transpose lambda represents the vector of reaction force at the generalized coordinates level. It is important to note that if we consider the friction and damping forces and also disturbances in the modeling, the Euler-Lagrange equation is written as equation 7. As you can see, these terms have been added to the Euler-Lagrange equation. In this equation, W is the power dissipation function due to the friction and damping, and tau this is the system disturbances. In this chapter, damping and friction at the wheel's rotation are neglected, so W is 0, and we do not consider disturbance in the modeling. Okay, let's come back to the equation 6. Using equation 6, a dynamic model of the constrained mechanical systems can be expressed in the matrix form, as you can see in equation 8. The final set of equations that is seen in equation 8 consists of n plus k differential and algebraic equations, actually n Lagrange equations and k constraint equations, and there are also n plus k unknowns in this equations set, n generalized coordinates and k for Lagrange multipliers, and we can denote that with lambda j, that j varies from 1 to k. Here you can see the dimension of lambda. Okay, let's once again fully introduce the components of equation 8. In equation 8, Q is a vector of generalized coordinates, and its dimension is n by 1. M of Q is a positive definite matrix of masses and inertia. The dimension is n by n, H is a vector of Coriolis and centrifugal forces, and also forces and torques due to the gravity. And its dimension is n by 1. S is input distribution matrix, and the dimension is n by m. Tau is the input vector, and its dimension is m by 1. A is a constraint matrix, and as we have seen, if we have k constraint, its dimension will be k by n. Lambda is vector of constraint forces, or we call them Lagrange multipliers, and its dimension is k. To eliminate the Lagrange multipliers in general dynamic equation, we can follow the following procedure. We remember from the kinematics that matrix G maps actions to the rate of pose chains. The columns of matrix G are a basis for the null space of A, so that A times G equals 0. The Lagrange multipliers in equation 8 can be eliminated pre-multiplying both sides of the equation by G transpose. This leads to the reduced dynamic model. If you write once again the equation 8, here you can see equation 8, actually the first row of the equation 8, and pre-multiply this equation by G transpose, the term G transpose times A times lambda will be 0, because in equation 9 we've seen that A times G equals 0. We can conclude that G transpose times A transpose is also equal to 0. So this term eliminated, and finally equation 10 is obtained. And equation 10 we have just m differential equations, and we cannot see any lambda. Now we develop a detailed dynamic model for a unicycle using a Lagrange approach. Generalized coordinates for a unicycle are x, y, and theta, and we denote this vector by q. So n is 3, and as we have seen before in the kinematics, the constraint matrix and G are as you can see in this slide. The kinematic inputs or actions for the unicycle are Vt and omega. Vt is the wheel's linear velocity, and this velocity corresponds to the driving input. And omega is the angular velocity, and this angular velocity corresponds to a steering input. And we can write the kinematic model as you can see here, and we obtained this equation before in the kinematics section. We define physical parameters as you can see. M is the mass of the unicycle, I is the inertia around vertical axis at contact point, and FVT is driving force, that is an input, and tau s is the steering torque, and that is another input. And the expression of kinematic energy is given as K equals m over 2 times x dot to the power 2 plus y dot to the power 2 plus half of I times theta dot to the power 2, and the potential energy is 0 because it is assumed that the robot moves in the horizontal plane, and the Lagrangian is equals to this terms. As you can see, the Lagrangian is equal to the kinetic energy. The other terms of Euler-Lagrange equation can be obtained, as you can see, time derivative of partial derivation of L by x dot equals mx double dot, time derivation of partial derivation of L by y dot equals my double dot, and for the theta we can obtain the time derivative of partial derivation of L by theta dot as I theta double dot, and we can obtain we can also obtain other derivations, and finally, according to the Lagrange formulation, the differential equations are obtained, as you can see in this red box. The obtained dynamic model can be written in the matrix form, you can see here, and comparing this matrix form with the equation we have obtained before, that was equation 8, the first row of equation 8, we can obtain these matrices. M is a 3 by 3 matrix, H is 0 here, and A is the constraint matrix. We know that from the kinematics, and S or input distribution matrix is a 3 by 2 matrix, and we can also obtain from the kinematics the G matrix, and as you can see, G transpose times S equals an identical matrix. Let's eliminate lambda in these equations. Simply by pre-multiplying G transpose to this matrix, we can do this. If we pre-multiply G transpose, we will see that finally these equations are obtained. You can see that the lambda is eliminated. Now I want to explain how to represent the state space model of the equations. As you know, this representation is very important in control. We have seen that the dynamic system can be described as equation 11, m of q times q double dot plus h of q and q dot equals s of q times tau plus a of q transpose times lambda. And the kinetic motion model is also given by q dot equals g of q equals v. Due to shorter notation, the dependence on q and q dot are omitted in the following equations. For example, we show m of q simply by m, and h of q and q dot simply by h. A time derivative of equation 12 will be q double dot equals g dot v plus g v dot. And if we insert equation 12 and 13 into equation 11, we will have m g dot v plus m g v dot plus h equals s times tau plus a transpose lambda. The presence of Lagrangian multipliers Lambda due to the motion constraints can be eliminated simply by pre-multiplying G transpose. So this term will be eliminated in the equation. Introducing M tilde equals G transpose Mg and V tilde equals G transpose Mg dot plus G transpose H, and also E tilde equals G transpose S, it gives a more transparent notation. M tilde V dot plus V tilde equals E tilde tau, from where a vector of accelerations V dot is expressed as the inverse of M tilde times E tilde tau minus V. If condition determinant of E tilde is not equal to 0 is true, which is in most of realistic examples it is true, then from equation 15 the system input can be expressed as tau equals the inverse of E tilde times M tilde V dot plus V tilde. By extending the state vector with velocities and presenting the system in nonlinear form, x dot equals f of x plus g of x times u, the state space representation of the system becomes as equation 17, in which you can see the dimension of the zero vector, and also you can see the input. Using the inverse model, the equation 16, the required system input can be calculated for the desired acceleration of the system. Applying these inputs to equation 17, the resulting model becomes as equation 18, in which UZ are accelerations of the system. A relation or equation 16 can therefore be used for calculating the required predicted system inputs. These inputs can be used to control the system without feedback, that we call it open loop control, and we will address it in the control section. And these inputs can also be used as feed-forward control in combination with some feedback control. We will come back to this later on the control section. Let's take an example. Consider a diff drive mobile robot. You can see its chassis and wheels on the slide. The front wheel is inactive, and the two back wheels usually powered by electric motors. Let us assume that the vehicle mass center coincides with the point A. The mass of the vehicle without the wheels is mv, and the mass of the wheels is mw. The robot moves on the plane, and its moment of inertia around the z-axis is jv. Z is the normal direction to the plane, and the moment of inertia for the wheels is denoted by jw. In practice, usually the mass of the wheels is much smaller than the mass of the chassis. Therefore, a common mass m and inertia j can be used. So we neglected the all the masses and the inertias for the wheel. The robot is described by or represented by three generalized coordinates, You can see here x, y, and theta. And its inputs are the torques on the left and the right wheel is denoted by tau L and tau R respectively. From kinematics, we have already obtained the matrices A and G. The expression of the kinetic energy of this system is given as you can see here. Don't forget that we have neglected the mass of the wheels. Here you can see the translational energy and the rotational energy, kinetic energy of the system. The potential energy is constant and is equal to 0 because it is assumed that the robot moves in the horizontal plane. The Lagrangian is expressed like this, and that is equal to the kinetic energy, and we can obtain the other terms of Euler-Lagrange equations as you can see. According to the Lagrange formulation, the equations of motions for this robot are obtained as you can see in the red box, where the resultant force on the left and the right wheels are as F equals tau L plus tau R over R, in which R is the wheel radius. The force in the x-axis direction is equal to tau L plus tau R over R times cosine of theta, and in the y-axis we should multiply this by sine of theta. And the torque on the robot is obtained by tau L minus tau R times d over R and is denoted by m. Therefore, the final model is, as you can see here, for the x direction, for the y direction, and for the z-axis. In the matrix form, the equations will be as you can see in the slide. You can see the M matrix, H matrix is 0, the constraint matrix, the torque distribution matrix, and also the G matrix. Note that the multiplication of G transpose and S equals an 2 by 2 identical matrix. The common state space model, equation 17, that includes the kinematic and dynamic model, is determined by matrices as you can see in this slide. Using the inverse model, the required input torques to the wheels can be obtained from the known robot velocities and accelerations. In this video, we talked about dynamic modeling using the Lagrange method. In the rest of this chapter and in the next video, I will talk about the formulation of dynamic equations according to the Newton-Euler method.